Hi there, welcome to your lesson on linear equations. On this opening slide, you can see three very different ways of writing a linear equation. By the end of this lesson, it is essential that you understand all three forms, when we can use all three, and how we can change between the forms. We are all very familiar with this form here. This is the most typical way of representing a line, y equals mx plus b. However, there's these two lesser known forms that we'll look at today. Let's get to it. So, forms of linear equations. I would highly suggest you take notes on the three forms we discussed today. So here's a line. Let's look first at the slope-intercept form. Again, the most common form of a line, y equals mx plus c, sometimes written as mx plus b. Here, in this form of a line, it is called slope-intercept because the m represents our slope or gradient, and the c or b value at the end here represents the y-intercept, therefore slope-intercept form. When we write a line in this form, we look at the line and we say, do we know the slope? Do we know the y-intercept? Let's check. Here, we know the slope. We can follow this line here. We have all these little slope triangles, rise and run. So it's going down 3 units and over how many? Okay, the slope is -3/4. And then you follow the line. Where does it hit the y-axis? That is our y-intercept. So I'm following this line. It hits the y-axis right here at the value of 2. Therefore, our equation is -3/4 x. This is our slope, down 3/4, and our y-intercept plus 2. That is slope-intercept form. Okay, now let's look at another form. And to find the next form of a linear equation, we begin with our slope formula, right? Our slope formula looks like this. Now, I want you to rearrange to isolate y minus y1. That means move this here over to this side so that only this is left on this side of the equation. When you do that, what do you get? It should look like this. I multiplied both sides by x minus x1 because that will get rid of it here in this fraction and it'll make it appear over here, right here. Slope times that. This is called the point gradient form of a line, and it comes from our slope formula. Okay, point gradient. So we use this form of a line when we know the slope and when we know some point. Okay, because this x1, y1 represents the coordinates of some point. And that point does not have to be the y-intercept, right? In this last form, we needed to know the slope and the y-intercept. Now, for this form, we need to know the slope and any point. Okay, so that's when we use this form. Let's take a look. Okay, so again, this is called the point gradient form. It looks like this. And in green here, this represents some point, and this m represents the slope. This is the same line I showed you a moment ago, so we know the slope is down 3/4, -3/4. And then you can select any point you want to substitute in for that. So I'm going to select the point 4, -1. That is this point right here, 4, -1. You could have taken any of the points. And then the gradient we know is -3/4. So by putting those into the equation, I am writing this. Y minus y1. Well, the y value of the point is -1. So y minus -1. Both negatives have to be there. Equals the slope, -3/4, times x minus the x value of the point. All right, the y and the x remain. In our equation, we need the y and x, right? Everything else has been replaced. Now, the nice thing about point gradient form is if you rearrange this, you will return back to your slope-intercept form. Let's try. First of all, these two negatives become a positive one here. And here, when I multiply -3/4 through here, I do -3/4 times x right here, and -3/4 times -4. The two negatives cancel, and the 4 in the fraction denominator also cancels with this 4. We're left with a 3. Now I'm going to take 1 and subtract it to move it to this side, and I get this equation. Now this should look familiar. This is the form we saw when we looked at this line in terms of slope and y-intercept. It's the same, and that's important to know. Just because we have this other form of a linear equation doesn't mean it's not identical to the form we've known. They are identical. They're just two different forms for the same line. Okay, so now with this problem here, I want you to do this. Look at the red line, purple line. Purple line is line 1. I want you to write a linear equation in gradient-intercept form, okay, or slope-intercept form. So in other words, just look at the line, find the slope, and then check the y-intercept, for example, here for the purple line, and then write the equation in this form. Okay, for line 1 it is this. The slope is rise 1, run 3. Rise 1, run 3. So the slope is 1 over 3. And the y-intercept we can see is at -3. There it is. Try the same thing for line 2. Okay, the equation for line 2 should be this. It has a slope of 4 units down over 1. 4 units down over 1. So slope of -4. And if you follow it, the y-intercept is here, 3. There's our equations in gradient intercept form. Now I want you to take each of those lines again and write the equations now in the other form we just looked at, which is called point slope form. So for point slope form, you will take the slope, which we already discovered for each of these, put it here, but then take a point other than the y-intercept and put it into these two values here. So starting with the purple line, line 1, what is the slope? And let's use this point here. So use this point and see if you can create this form of the line. And then simplify that to see that you arrive back at this equation. Okay, so here I put in the slope of 1/3 right here. And then into y1, x1, I put in that coordinate we chose here, which is 6, -1. So 6 and -1. If you simplify this, you should arrive back at this. Let's check. -1 and two negatives here make a positive. Here, if you multiply through, you get 1/3 x and -2. And then you're going to subtract 1 because you have a positive 1 here, and you get this. You arrive at the same equation, which is great. Try the same thing for line 2, the red line, and use this point here. Okay, here is our point slope form. We have our slope of -4 again, and then we put in this point here, 2, -5. So you can see here -2 and then -5 here. That simplified becomes this and then this, which brings us right back to here. It is really important that you see the connection between these two forms and you're able to algebraically do all this. Pause if you need to. All right, let's look at the third form of a linear equation. This is called standard form. Standard form looks like this. ax plus by plus c equals 0. Okay, here's how it works. Let's say we begin with our slope intercept form for this line, or basic form. I'm going to change it to look like this in standard form. In standard form, notice that there are no fractions. This a and b values must be whole numbers. So here I have a fraction. I'm going to multiply everything by 4 first to get rid of this 4 in this fraction. Okay, and when I did that, I get this. 4y equals -3x plus 8. Everything's been multiplied by 4. Now to get into standard form, I need to move everything to one side of the equation, trying to keep these to be positive. Alright, so I'm going to move 3x over there by adding 3x and -8 over there also. So I end up with 3x plus 4y minus 8 equals 0. I cleared everything from this side. There is standard form. Okay, so just to recap, we had slope-intercept form, looks like this, where we have slope and y-intercept. And then we had point gradient form, where we had the slope also, but then some other point put in here. And finally, we have standard form, which looks like this. Remember that you can always begin with this form and change to the others, or usually begin with this form, change to that one like we've been doing, and then that can then be changed into this. Okay, let's look at some problems like this. We have, it says here to find the equation of each line in gradient intercept form. So it wants the equations in this form, our most basic form, and we have a line with a gradient of -2 and a passing through the point -4, 3. Now, if we want to write it in this form, we need the gradient, which we have right here, gradient, and we need y-intercept. This, however, is not the y-intercept. So what we often do is begin in the other form, the point slope form, and then change it to this form. So try point slope form for this one, and then change into that. Okay, so here's point slope form. Put in what you know. Put in a slope of -2 here. Put in your x and y values that you know here, -4 for x and 3 for y. Rearrange that just a little bit. Okay, I'm going to combine those to make +4, but then multiply by -2. Then move the 3 over, you get this. Now this is in this form, so now we know that this line passes through this point, but we know it also has a y-intercept of -5. Now, before we move into question B, I want to look at question A another way, because there's another way that's commonly used, and you might prefer it. It's good to know there's options and different ways to approach things. In their first approach, we began with this, the point gradient form. But what if we wanted to begin with this form, with the slope-intercept form? Can it be done? Let's try. So here's our slope-intercept form. Again, I use C instead of B. That's interchangeable. All right, we're going to put in what we know. We know the slope of -2. So I'm going to rewrite that with a slope in there, replacing M. But we don't know C. We don't know the y-intercept. So how can we proceed? Well, we are given a point. So why don't we put the point we know into this equation? And the point we know represents an x value and a y value. So we can actually replace the y value and the x value here in order to solve for C. So I'm putting the point -4, 3 into it. Y becomes 3 and x becomes -4. So I've replaced the values there. And now I have an equation with the only unknown being C, so I can solve for C. Okay, multiply -2 times -4, you get 8. 3 equals 8 plus C. Subtract 8 tells you C must be -5. So that brings us back to where we were here. Now you know C is -5, so you know that this equation here must be -2x, and then C, whoops, that's a mistake. There, I've made that change, and we know C is -5, so this must be -5, and notice we have the same thing. A lot of students prefer this approach, but I want you to consider both and understand you have flexibility. So now let's move on to question B. In B, we are given 2 coordinates that a line passes through. We are not given the gradient. That is important to note. Whether we begin in this form or this form, we need gradient in both, right? There's M here. So we always need gradient before doing anything else. So look at these 2 points. Always find the gradient first. What is the gradient of a line that goes through these two? Use your slope formula to find a gradient. So using the slope formula, y2 minus y1 over x2 minus x1, right? We're subtracting the y values, subtracting the x values to find a rise over run. You should get -1/2. So that's the first step always. Now we have the gradient. Now you have a choice, either this form or this form. Pick the method that we used here that you prefer to find the equation of the line. Well, I chose this approach again here. I put the slope in there, -1/2, and I put k instead of C. It's strange, that letter just changes all the time. C, B, K, whatever you want. The fact is, it's the y-intercept and it's unknown. So then we plug in the point we know, which in this case, it looks like they took the point -2, -1 and put it in here for x and y. You could have used 6 and 5 also. Know that you can use either of the 2 points. And then that allows you to solve for k. Therefore, you have the equation here. All right, hope you had some success with that. Let's keep going. Here's another problem here. Find the equation of a line that has gradient 3 and passes through this point. So very similar to what we just did. You know the gradient, you know a point. What is the equation? All right, here's the answer for A. Here they used point gradient form. It has not been simplified any further. You can, of course, multiply this by 3 and then move the 7 over. Also, it's showing you that you can graph that. But it says to graph it on your calculator, you always do need to change it to this form. All right, you need y equals form. This is the slope-intercept form. So that was multiplied and the 7 was moved over to get this form, and that can be graphed. And when you see the graph, you can confirm everything makes sense. It has a y-intercept of 4, great. And it has a slope of 3, rise 3 over 1. Great, now try B. You are given 2 points. You need to find the equation. Okay, remember with 2 points, you always need to find the slope first. So here's the slope of 2, and here used again point slope form. So here's the slope, and then the point that we know, one of them, 1, 3, was put in here. All right, again, that one can be graphed like this. Okay, let's try graphing another way. It says draw this line, and this is given to you in standard form now. You may recognize this in standard form. Everything on one side equals 0. It says draw the line by plotting points. Okay, by plotting points. So instead of rearranging the equation and looking at the equation to graph, we're just going to get some points, because once we plot some points and connect them, we also have the line drawn, right? So first of all, well, yeah, let's rearrange this so that we solve for y. Rearrange it so you have y equals something. What will it be? Well, I hope you got this equation here. And of course, from this equation, we can graph it, because we know the slope and the y-intercept. But how about plotting some points? Okay, again, we have the slope and we have the y-intercept, so we could simply plot the y-intercept, use the slope to make the line. But in this case, we're just trying a different approach. Let's use these values for x, put them into this equation, and get some y values to complete this table here. Well, the y values you should have are 3, 0, negative 3, and 6. So now we have a bunch of coordinate locations. Negative 2, 3 is one point, negative 1, 0 is another, and so on. Plot these 4 points and connect them to make your line. So here are the points plotted, and here's what the line should look like. And again, it matches what we saw in our equation here with a y-intercept of negative 3 right here, and then a slope of negative 3 as well. It goes down 3 over 1, down 3 over 1. Everything looks good. All right, how about this one here? It says we have points A and B which lie on the boundary line between two plots of land. So imagine this is one land plot and another one here. Write an equation for the line passing through these points. Okay, and then it says, well, first of all, we're given 2 points. We need to make an equation. So remember, when we're given 2 points, you need to find the slope first and then write the equation. And then it says, once you have the equation, a tree is located at this point, and determine whether the tree is on the boundary line. So write an equation for this boundary, and then check if this point works in that equation. If that point works in the equation, and by works I mean if you plug the point in for x and y, the equation ends up looking balanced. Everything equals something else that's the same thing. Let's try. Okay, so here's our slope first of all. Between these 2 points, we have a slope of 1 over 3 using the slope formula. But of course, we could also check on here. Rise 1, run 3. All right, that's our slope. Now, this is our equation. This is our slope. Here's our y-intercept. Clearly on this graph, we can see a y-intercept of 6. Of course, you could have used the form where we plug in a point and check for that, but here we are. Okay, now that we have the equation, we are putting the point 25, 30, that tree location, into our equation. So y is replaced by 30, and x here is replaced by 25. Now we're going to check if these two sides are actually equal to each other. And in this case, 30 does not equal what this becomes, which is 14.3. Since that point doesn't keep balance in the equation, we know the point is not part of that equation. It's not part of that line. So we've answered the question. The tree is not on the boundary line. Okay, try this one here. Similar problem. We have a sailing boat moving along at a straight line, so it's following a straight path. Here's the equation given to us. That looks like standard form, except we have 3 here. And so you know, standard form often has the constant put on this side rather than the other side with the 0. But anyway, this is kind of standard form. All right, determine whether a tanker located at this point is on the trajectory of the sailing boat. In other words, if the boat keeps following this line, will it hit this tanker that is at that location? Approach this like the last problem. Put this coordinate into the equation and see if the two sides are equal to each other. Okay, and then hopefully you tried B as well. Here's A. So the point 3, negative 2 replaced the x and y values here, and we ended up with something. We have negative 9.5 on that side. On this side, negative 9.5, and that does not equal 3. So the boat is not going to hit the tanker. In question B, we are looking for the y-coordinate of the port if the x-coordinate of the port is at 10. So we put 10 in for x here into the equation, solve for y, and we have the y-coordinate of the port. Okay, next, a quick recap of horizontal and vertical lines. It's something we looked at in a recent lesson, but let's recap. Here's a horizontal line. It has slope of 0, right? But the equations of horizontal lines always look like this. Y equals some value, and that value is whatever y value this line is going through here. So for this one, the equation is y equals 2. That is a horizontal line. Vertical lines look like this. Their equations are always given in the form x equals some value, because in this case they pass through some x value here. In this case, the equation is x equals 3. So this is the full equation for this line, and this is the full equation for this line. That will be useful in this problem here. So here we have a country road which is straight, and it has this equation. It intersects 2 state highways, and the 2 highways have equations x equals 0 and y equals 0. Think about that for a moment. This is a vertical line, this is horizontal, but where are they specifically if we were to graph them? 0 and 0. Oh, those are like the X and Y axis. Okay, so we have two highways at the X and Y axis and this country road. A beverage shop owner wants to open two new shops exactly at the intersections. So draw the graph and then find the exact locations of the two new beverage shops. And finally, find the distance between the beverage shops. So let's break this down. First, there's your graph. Check your graph. Do you have that? This line here has a y-intercept of 11.5, which you can see here, and a slope of negative 0.75. So you can go down 0.75 over 1, down 0.75 over 1, and so on. Or more easily than that, I think easier than using slope to graph, we begin with the y-intercept and then take any x value you want. For example, 6. Put an x value of 6 in here and see what y value you get. So 6 goes in there, we get a y value of 7. That gives us a second point, and then we can connect and draw the line. So there's our line. This is the country road. These are the two state highways, because this is x equals 0, and this is y equals 0, horizontal and vertical lines. So what are these points exactly? Well, the way to find those points is you can say, hey, when x is 0, what is y? Well, we already know that. That's the y-intercept, 11.5. But what about this one? We want to find the precise location. We don't know exactly where it crosses, but we do know this is the line y equals 0. So why don't we take this equation, make y 0 here, and then solve for x. It will tell you what the x coordinate is right there. Try that. Okay, if you do that, you make the y value. Oh, sorry, I'm showing the first part again. If you make x 0 here, you solve for the y value, which is your y-intercept. And now we're going to do the opposite. Make the y value 0 right here. Put 0 into the equation, solve for x. That is 15.3. Gives you the exact location there. All right, so now we know where the two beverage shops are. How about the distance between these beverage shops? So distance means, use the distance formula from our last lesson, or not last, but recently. Distance formula. What's the distance between those 2 points? All right, here's the distance formula applied, or you can think of it as Pythagorean theorem, right? So it's this squared plus this squared equals hypotenuse squared. So hypotenuse is being solved for 19.2. All right, a couple more. Draw the graph of these two lines here. First one looks like this. Second one looks like this. In this case, we could have used the approach we just did in this last problem. It's very important to know when you have a line in any form, you can find the x and y intercepts by making x 0 and making y 0. So same thing here. We could have made x 0 here, and if x is 0, this disappears, and solve for y. And then we get this value right here, this point. And then we can make y 0 in here. So make this 0, and then solve for x, and that gives you 2. Connect those 2 points, and you have your line. That's one way to graph that. Of course, you can also rearrange the equation to y equals something, 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 and graph that. This one here is already in slope intercept form, which makes it easier to graph. Slope and intercept of 4 right here. All right, last question, I believe. We have two straight roads with these two equations. They meet, and there will be a traffic light installed at this intersection. Find the coordinates of this intersection point. In other words, when does this line equal this line? Set these two equations equal to each other and actually find the coordinates. That's what it says by by solve it algebraically. You set the two equations equal to each other. This thing equals this. By doing that, you're saying, when is this line intersecting this line? Solving this algebraically gives you x value of -2. And when we know an x value, we can put it into either equation and get the y value. And that y value is 9. Confirming that by graphing, here's the graph, and we can see that those two lines meet at that point. It matches what we found algebraically. Great job. I hope you have a better understanding of lines and you feel comfortable with these processes. We'll see you soon.